at a certain pH of 3.50. Okay? So I've given you, so visualize this. I've given you 200 milliliters of a 0.1 molar solution of hydrofluoric acid. Okay? So you already have that. I got to figure out how many moles, and then we convert that into grams, of potassium fluoride I would have to add to make it a buffered solution with a pH of 3.5. So, first off, does it have the two things that I need to be a buffered solution?
Yes.
Yes, I've got the weak acid, hydrofluoric, okay? And then I'm going to add the anion, okay, off of the potassium fluoride, onto that, so now it becomes a buffered solution. So, here's the easiest thing to do, is to start with that Henderson-Hasselbalch equation, okay? So, you've got your pH equaling your pKa plus the log of your anion concentration divided by the concentration of my acid, right? Cool with this, all right? Now, here's the deal. Where are you going to put the 3.5?
On the pH.
It's my pH. Okay, so I've got that. Okay, so I know that number.
You got it.
How can I find my pKa?
Look at
Oh,
the
the
K.
negative log of the
Okay, so somebody find the negative log. So find the Ka of acetic acid. I'll save you some time. It's 3.17.
Negative 5.
It's 3.17. I forgot that I had it written down. Okay?
Wait. Oh, is the
Oh, is that the pKa, not the...
Okay, now let's before you do any math, okay? This is just if you take the negative log of the Ka of acetic acid, this is what you get.
Wait, acetic?
Huh?
Acetic?
No, I'm saying hydrofluoric. I'm sorry, hydrofluoric, my bad. I'm used to saying acetic. So here's the deal. Before you do any math at all, okay? Is this, what do you know about this ratio here? Is the ratio of the anions to my acid, is the anion concentration going to be bigger or smaller than the concentration of the acid?
Bigger.
because it has to get to 3.5.
Yeah, because this, what I add here has to be a positive number, okay? So, because if it's the same ratio, 1 to 1, oh, then it's just 0 on my pH equals my pKa. So, this is why when you're choosing buffered solutions and you're choosing which acid to start with, choose an acid that's close to what you want your pH to be. If I want to make a solution with a pH of 3.5, I don't want to start with a pKa of 8, okay? It's stupid. Because I'd have to drop it from 8 all the way down to 3.5, okay? 3.17, hey, that's not bad, okay? I can live with this, okay? I can tweak it a little bit, okay? So this is why it's important when you're making buffered solutions that you choose wisely in terms of which acid that you're going to start with. Okay, so here's the deal. So of these numbers, what else do I know? I know the concentration of my acid, right? So it's the only thing I'm not going to know.
Your anion.
My anion concentration. So here's the question, how am I going to get that by itself? What's the first thing I'm going to do?
Subtract 3.
Subtract minus 3.7, which is going to get you 0.33, right? Equals the log of your anion concentration divided by 0.1. Now what?
Separate the logs.
How do I do that?
Do the subtraction
Subtract.
technique. Log of A minus log of HA.
Well, how about this? Let's just get rid of the log. How can we just get rid of the
10
log?
to the 10.
Yeah, let's just take 10 to the 0.33. Now, don't take 10 to the negative 0.33. Okay? Okay? Do not take 10 to the negative 0.33 because this is log. There's no negative in front of it. Okay? This is just a straight log. Do not take 10 to the negative 0.33. Okay? Don't do it. So, you do that. Somebody take 10 to the 0.33.
2.14.
Okay? So that's 2.14 equals your anion concentration divided by 0.1. So then multiply that across, I get
0.04.
0.214 as my anion concentration. Now, here's what's important. That's molarity, okay? That isn't moles, that's molarity, right? Now, at this point, if I were to make an entire liter of the solution, okay, this is important. If I were to make an entire liter of the solution, I would need 0.214 moles. That's what that means. I don't want to make an entire solution, or an entire liter of this stuff. How much do I want to make?
100.
Just
I only want to make
200 milliliters.
200 milliliters of this stuff. I don't want to make an entire liter. I only need 200 milliliters of it. So there's a couple of things that you can do depending upon your preference. One option is you can go, okay, that means that I got 2.41 moles per 1,000 liters, or excuse me, per 1,000 milliliters, which is going to equal X number of moles over 200 milliliters. Okay? You can set it up as a ratio, because this is what this means. I got this number of moles per 1,000 milliliters, which is a liter, which is going to X number of moles over 200. You cross multiply and you divide. Okay? If you like ratios, do ratios. The other thing that you can do is just a straight stoic problem. You go, okay, hey, I got 0.214 moles per 1 liter. If I multiply that by 0.2 liters, the liters cancel out, I get moles. Okay? So, I don't care how you understand this, but here's what you do have to understand. This is the number of moles you have per 1 liter. Okay? And we're not making an entire liter, we're only making 200 milliliters of it. So, if you do the math, you get, what do you get?
482 molar.
What'd you get?
0.428 molar of the
Now,
0.0, yeah.
0.0428. Now, that isn't molarity. That's moles at this point. Okay? That is not molarity. Those are your moles. Okay? Those are your moles. So I've got the first part done. So now, this is the moles of potassium fluoride that I've got to have. Okay? Because it's going to ionize in a 1-to-1 ratio. So, here's the deal. Now I've got to figure out how many grams I've got to have. So now this becomes a Chem 1 problem. I got 0.428 moles of potassium fluoride. Now, here's a common mistake that people will make. They're going to go, oh, I'm just going to use the molar mass of the fluoride ion. Okay, you cannot go into the chemical storeroom and grab a bottle of potassium fluoride ions. Okay, you go in and you grab a bottle of potassium fluoride that ionizes to produce that amount of fluoride ions. But you cannot isolate and go into the chemical storeroom. I'm never going to send Bruce into the chemical storeroom and go, hey Bruce, go grab you a bottle of fluoride ions. Okay.
We have fluoride in the water. Well, not here, but other places.
Well, but that's, okay. So anyway, you look up the molar mass of potassium fluoride, that's 58.1, so you get 2.49 grams of KF. Okay, so that's how many grams of potassium fluoride you would add to the 200 milliliters to end up with a solution that has a pH, a theoretical pH of 3.50. So that's what you're going to have to be able to do on the assignment and also on the lab tomorrow. Okay? So, shut that down and then bring the camera with us. You can unplug it and then we're going over